well, this frequency in this simulator can simulate up to very high frequencies. That's the key attraction of this simulator. There has been, we discussed in the theory class that in the past, people were always using the low frequencies. I mean, it was in the gigahertz, but not the higher range of gigahertz frequencies. And the reason was the lower the frequency, the more convenient it is, the cheaper it is. But simply because we have now the lower frequency is more mostly occupied, and also we need to accommodate very wide bandwidth for some applications. Okay, so for these two purposes, higher frequencies, we have to just resort to high frequency use, and even very high frequency use. So recently, some bands have been defined for. I'll share these band names in the theory class. D band, G band, E band. Different bands have been defined for very high frequency use. Okay, so commercial deployment for very high frequency use, and more interestingly, there have been definitely used in 30-40 gigahertz range. There was some use for satellite communication, okay, which requires very wide bandwidth. But that was LOS communication. But with the 5G cellular deployment, people have started using high frequencies for non-LOS cases, okay, which is sort of beyond imagination before. And also people are, in 5G, people currently are looking at the use of frequencies up to 100 gigahertz, we know, but beyond 5G, people will be using even higher frequencies, say in 6G, or a far-sighted vision actually includes frequencies beyond 100 gigahertz. Now, this particular tool supports up to 150 gigahertz. Okay, so that is really amazing, and we are sort of fortunate getting this kind of tool for free. Of course, high frequency tools are there. Many high frequency simulators are there, but they are not available for free, except this one. This has been mostly developed in the academia, and so it has been made free, and it's open source code. Okay, this tool mostly depends on experimental data. A lot of tests have been made, and based on the experimental data, they characterized the output performance. Okay. However, the support of frequency up to 150 gigahertz currently applies to only indoor cases. Okay, only the cases where you consider the inside of a building, okay, or in building coverage. If you consider outdoor environment, or all different types of conditions, then the support is up to 100 gigahertz. So 5G is fully covered anyway, And for in-building coverage, the frequency support actually goes beyond 5G. Okay. Well, almost all of you have joined already. Uh, well, Haidar, are you there? And the first, I mean, there are, you know, that we are few teachers with this lab course, and I can see Ibrahim Mubarak has joined already. Haidar, are you there? Okay. Ibrahim, can you collect their attendance? I
Yes,
think
sir.
I think
Assalamu
it is.
alaikum, sir.
Walaikum assalam. How are you today?
Good, sir. Better.
Alhamdulillah. Okay. So I think it is. What do you think, Ibrahim? I mean, should they? I mean, write down the instant number on the Google Classroom. I mean, if you create a question, is it the best way?
That
What do you
is
think?
I think I will take it manually. It's better so that I
Okay.
can check.
Okay.
I can
Okay.
check.
Okay. Then maybe we do it after we complete the demonstration. Okay.
Yes.
Because
Maybe during the demonstration I will do it because some
okay.
students may
Okay.
during.
Okay. 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 Sounds good. Uh, okay. Now, the students, were you able to install the tool Nyusim?
Yes, sir.
Yes.
Okay. Okay. The tool is not that user friendly, you know, because it is a free tool. Uh, it's not. I mean, commercial tools always have some advantages, which we cannot get. Like the tools sometimes create problems in. I mean, if when you wanted to run repeated simulations, okay. So, but these things may have been resolved in these recent versions. You know what? I didn't work with this latest version much, so I mean, I may get stuck somewhere. Okay. Also, I mean, I may not answer uh, some of your questions. Okay. I mean, don't ask me too hard questions. Okay. I'll be demonstrating. Uh, well, if you yourself go through the manual, then probably, I mean, you can be an expert. Okay. You can learn it better than I do. Okay. But let me tell you what it does. It basically creates the PDP, power delay profile. Okay. Also, it shows path loss exponent. Okay. We know what path loss exponent is. I mean, it can show you the path loss for the environment, and more importantly, it can create PDP, power delay profile. So it simulates the impact. Yeah.
Hello, sir.
Yeah.
So your voice is getting cut off
Oh,
sometimes.
really?
Yes.
This may be due to my internet connection.
Sir, but I am hearing it clearly.
Yes,
You
sir.
are?
I'm
Sir,
hearing
right
fine.
now it's okay, sir. Like
Right
right
now,
now.
it's
Yes, sir.
okay.
Right now it's okay. Yes.
Okay, please let me know if it again gets problematic.
Okay.
Okay. Well, we know what power delay profile is. You generate an impulse from the source end, and at the receiver, you will get different versions of it. Okay. So you put it at their respective delays. of, different versions are supposed to arrive at different moments. So show them with their respective delays. That is what we have power delay profile. Okay, so it is channel impulse response. It is channel impulse response, or CIR, right? We didn't use this term in the theory class. Actually, we we should have used. This is something not specific to wireless. Many actually models, okay, are represented by their channels impulse response. But what we showed in our PDP, or what we discussed in the static part or first part of our feeding, okay, basically was channel impulse response. We use different arrows at different delays. Okay, so those were the impulses in the time domain. Well, so this tool will be showing channel impulse response, and also it can simulate motion or mobility of the user. So the user will keep moving as it simulates over a time period. It will keep moving. The user is called here user terminal, okay, or UT. And the UT will be changing its position, okay, moving at a particular velocity uh, at some particular intervals, which they call segment. Okay, so at some intervals or segment ends, it recalculates the whole thing. Okay, so it will be showing the PDP for many different positions. And for this purpose, the graph, output graph, will be three-dimensional. Okay, PDP for many different positions throughout its motion. Over the environment, we have some control. We can set different things. I'll show you, like how the temperature is, how much the distance between the transmitter and the receiver, whether how much attenuation you have for the foliage, okay, the antenna conditions, kinds of array you are using, and also there is a feature which shows how you consider the change of environment throughout the motion. Okay, there are two methods to consider a variation of environment or propagation, multipath propagation environment, okay, or the channel, multipath propagation channel. So we these two methods are called drop based and spatial consistency. Okay, drop based, and spatial consistency. Okay, in the case of drop based, the tool generates the environment. Well, we know that the multipath propagation environment is actually very difficult to predict, and it is sort of random, right? And we also mentioned in the theory class that at slightly two different positions, you will have differences in the signal reception, or at the same position over time, okay, at two different moments, okay, which are close to each other. Okay, you have some difference in the reception. I mean, momentarily, the reception changes. So it's all because of the random or unpredictable constant variations of the multipath environment around. Now, in the case of drop-based method, at every segment end, we are saying that it generates the output for every segment part. Okay, so for every segment, it consider the environment. I mean, it consider the generation of the wireless environment or multipath environment independently. Or I mean, the simulator actually, assumes some environment and finds out the output for this particular environment. The environment, the simulator itself will keep generating. Now in the drop-based case, at every segment, it generates independently. But if it is spatial consistency, then it generates with some correlation with the previous segments. Okay, and it makes sense for most environments. Well, if I mean the environment will not change too much rapidly in short time intervals, the multipath environment should not have an abrupt change. Okay, the I mean uh, abrupt change is not likely. Okay, so if you use some correlation as you create the new multipath environment, okay, then it can better represent the environment. All of these things are done to to get an idea how the output might be. The real environment is difficult to simulate properly. Okay, so just try to make it as closely as possible to the real condition. So in that case, spatial consistency, please.
Parosh Bhai,
Yes.
are you here? Okay, so it's back.
Okay. Oh, Haider, are you there?
Yes, sir.
Okay, how are you doing today?
Alhamdulillah.
Okay. Well, so we are still having an introduction to our new tool. So spatial consistency can be actually more logical for most cases. However, the drop-based mode is still there as a feature because in some cases it can better represent. Like if you have a very fast vehicle, user who moving very fast, okay, then the application of spatial consistency feature may mislead. Okay, your environment is changing too fast. So in this case, the drop-based mode can rather give your results close to the real scenario. Okay. So this spatial consistency feature you can turn on or turn off. Okay, now let me share the screen. Okay. Now you know what I can. I mean, the tool may not work properly in some cases, and I may get stuck somewhere. So I'm nervous now. Okay, so first you start this way, hitting the button start. You then get all the different options. Okay. On the right side, you can see the spatial consistency parameters, and on top of that there is on and off features. So you can turn off the spatial consistency, okay, or you can turn on. Also for human blockage, okay, well, this this tool mostly focuses the cellular application, okay, although it probably doesn't say explicitly. The consideration of the environment is exactly like what we have for cellular environment. Okay, you have some mobile device, the receiver is moving, whereas the base station has a, or the transmitter has a fixed position. Okay, so downlink for cellular environment is the is what you should keep in mind. Now, for cellular environment, the environment is shown with different terms. On the left corner, you can see the drop-down menu has UMI, UMA, RMA, and in H. Okay. The first one should I write down? Probably, I mean, you can remember. Also, these terms you'll find in full in the manual. Okay. UMI means urban micro. Later you say urban macro. The difference between micro and macro is that the cell size is medium in the case of micro, and in the case of macro, the cell size is large. You have a large coverage area. The base station transmits with a high power, and then it is called a macro cell. But if you use a medium size antenna, it is called a medium size cell, it is called micro. Okay, and of course there is also pico cell and FM2 cell, or very small cells are concepts are there. But anyway, they consider here macro and micro. Now the environment can be considered to be urban. Urban means you have a lot of buildings. So the buildings are cluttering up the area. And of course, this environment is a lot different from a rural area where you have sort of open space, very few obstacles on the way. So urban micro, urban macro, UMI, UMA, and RMA, rural macro. Okay. Rural micro models are not used. It is always considered that in rural areas, you'll be using large cells. The cell size depends on the user density. Okay. The higher the user density, the smaller the cell size should be. These things we'll shortly discuss in the theory class. So the cell size is always considered large in rural areas because the user density is very low. The fourth one is in house actually. Okay. It is for office or commercial buildings. Inside commercial buildings, this particular environment, wireless environment is considered. And for the first three scenarios, the maximum frequency is 100 gigahertz. But as I said, for the in-building coverage area, for the fourth option, in H, the maximum frequency support is 150 gigahertz. So let us work with urban micro first. Then the carrier frequency you can set from here. You can see that the frequency can go up to 100 gigahertz. Let me show you that when you set in H, the frequency range is up to 150 gigahertz. Okay. And 5G starts from 500 megahertz frequency. So you see it is from 0.5. Okay. That these things confirm that they always keep the cellular environment in mind. Okay. The bandwidth for operation, you see, they are considering, they are allowing the bandwidth to be up to 800 megahertz. Okay, which is, cellular environment applications will not use this large bandwidth even in another century. Now we are, well, even we discussed the carrier aggregation, okay, which is a very rare use that can go up to 100 megahertz. And well, but nobody knows. I don't know. I mean, the situation may change too much. Okay, so I think I should retreat for my from my statement that it won't go. It may. Anyway, the distance range option. Below that, you'll find what distance you want to specify between the transmitter and the receiver. So in the it gives a lower bound 10 meter and upper bound 50 meter. So the user will be moving within this range. Okay, the user will have a motion as the simulation runs, and the motion will be within this range of distance 10 meter and 10 meter through 50 meter. Well, but if you want to take very large range, okay, you can do that. This current option allows you to set here some distance up to 500 meter. So you can set actually 400 or something. All these things will give you correct result. I mean, these are valid. You can maybe we go back to this 50 meter for now. Now you can see that you can have even larger distance, 10,000 meter or 10 kilometer. Why is it 10 kilometer? Oh, okay. The maximum support is 10 kilometer. Well, let me tell you that the maximum cell radius, okay, or the maximum distance considered for 4G specifications is 100 kilometer. But people don't use that large cells. Okay, that is the maximum cell size or cell radius or maximum distance allowed for 4G between transmitter and the receiver, 100 kilometer. But in practice, people don't use that large distance. Here it supports up to 10 kilometer, which is the practical largest distance. Now, the environment, you can consider LOS or non-LOS. You can set it. And then the transmit power from the base station, you can set from here. Station height, we should set it higher. The typical base station height is 20 to 30 meter. So let us set it to 25. The user terminal height, in the phone, you may be a pedestrian, and then your phone will be at a height when you are talking. Okay, that depends on your own height. Okay, if you're very tall, then I think they have considered 1.5, which is, well, okay, we keep it like that. You should set it depending on whether you are tall or short. number of RX locations. We have just one, okay, but you can simulate with higher number of receivers in the cell. And the atmospheric condition, temperature, humidity, the pressure, these things affect slightly to the path loss. Okay, you have little bit absorption of energy on the way, and that depends on temperature and pressure a little. Okay. But these losses are very small. Polarization, we discussed polarization. I mean, what it is. Copolarization means when you have matched the polarization between the transmitter and the receiver. The receiver antennas are oriented the way they should be, or aligning with the antenna position of on the transmitting side. So then it is copolarization, and we will be doing our simulation with this setting. However, if you set it the other way, I mean, cross polarization means completely orthogonal position for at the receiving end. We probably mentioned that you'll still get some signal, okay, for various reasons. I mean, first of all, the antennas are, I mean, the antennas don't behave ideally here. That orthogonal position will not allow any signal reception. Okay, so that is ideal, but practically you have some reception. Secondly, the non-LS environment takes the signal with different forms. Okay, I mean, the polarization for the different versions are not alike. Little bit, I mean, you don't have that strict requirement of polarization in non-LS environment. So cross polarization can also allow you signal reception to some extent, and you may want to check it for some reasons. Okay, the receiver, you may not have good control over your receiver position, so you may want to check when you are not perfect holding it with perfect alignment. So how the signal reception would then be? You may just wanted to know. Okay, maybe you are holding your phone with some tilting or inclination that matches the base station antenna position, and then copolarization will give you proper result. But what if you put it in a wrong position? Okay, so you can check how much signal reception you may have then using cross polarization. Foliage loss, okay, you can just say whether you have it or not. Distance within foliage, foliage attenuation. Well, a lot of things are there. Iteration outdoor to indoor loss. These things indicate that whether or not you are inside a building. Okay. If you are inside a building, then set it to yes. You have O2I, outdoor to indoor penetration loss. Okay, which simulates the actual, which is also called BPL, building penetration loss. And once you have that, you can set whether you have low loss or high loss. Okay. In the theory class, we showed the building penetration loss for old buildings and new buildings, and showed the actually two distinct conditions of low loss and high loss. Okay, low BPL, high BPL for two different types of buildings. So similarly, you can set low loss or high loss. Then antenna properties. Well, on the transmitting and the receiving side, ULA, URA. I mean, this means uniform, linear array, uniform, rectangular array, Well, well, I can go online and show you, or you can just do it yourself. You know what array is? In the case of array, we have multiple antenna elements working together like one antenna. Now, it's up to the designer how he arrange the different elements. Okay, a lot of times you have a, I mean, an area, okay, rectangular shape of area where you have rows and columns for different elements. However, in this case, it is not actually filled up an area. You rather have the antenna elements located on some straight lines. When you say uniform linear array, then you just have one line. Okay, so a number of elements will be just put on a straight line. And uniform rectangular array means you have a rectangular form, and along these four arms of the rectangle, so again it's actually a straight line, you put different antenna elements. Okay, you can see the figure. If, well, maybe I go online and find it out for you. UCA means you put the different antenna elements on a circle. Okay, so uniform circular array. Maybe I give me a second. Yeah. You see the black dots on the, I mean, note down this part. On the left side, you have ULA. Then it is URA. And the rightmost one is UCA. Okay. The term uniform comes from the fact that the distance between all the antenna elements is the same. It doesn't vary. Okay. So anyway, we did not actually discuss antennas in detail, but could you see the figure in this part? Was it visible?
Yes,
Okay.
sir.
Okay.
Yeah.
Thank you. Thank you. Well, this part is not too important for us because we did not discuss the antenna operations. The number of antenna elements, you can see it, the spacing, I think spacing between the antenna elements. Number of TX antenna elements per row. Okay. Well, maybe it allows multiple rows. Okay, this kind of say ULA you have, but multiple straight lines. Okay, with antenna elements may be allowed. I'm not quite sure. The number of antenna elements per row. I'm not quite sure what these fields tell you. Then TX antenna azimuth. Azimuth means the horizontal angle made with the direction of north. Okay, like east, the pure east has an azimuth of 90 degree. Okay, the west has an azimuth of 270 degree. Okay, probably I understand what it is. Sorry, it's actually filled for HPBW. Okay, that we know, right? the half power beam width for antenna. So it is giving you the antenna radiation pattern, or the actually sort of representing the gain. Okay, how directional the antenna radiation pattern is. Antenna elevation. Well, you can have some tilt compared to the ground, like the antenna element at the whole antenna at the top of the base station uses a down tilt. It faces little bit, it is little bit downward. Okay, because you have a, you need to cover many people, okay, over an area, spread over an area. So from a high position, then you need to send signal. But then you should, I mean, the antenna should face towards the people. Okay, because the position of the people is at a lower height, is at the ground or in some buildings at a lower height. Okay, so it should face. I mean, people are not flying. People are not flying right in the sky at the level of the base station. So
So why we put the tower heights that high? I mean, if I eventually direct the antenna towards the people who are actually in lower level, so why we go upwards actually for antenna placement?
Well, you don't you don't set it at a high position inside a building for Wi-Fi. You don't set it at a high position. You set it at your own height, right? That you do. But when you cover a large area, then it is like well, maybe we discuss this way. Say, at your home, level of your lights are pretty much at the same level where the people are. Okay, almost at the same level. But consider the stadium. Okay?
Oh, yes, sir.
In the case of stadium, if you put if you put these lights at the level of the players, it how funny it would be, right? So from high position, but of course these lights have some down tilt. Yeah, it uses some down tilt. It faces towards the ground.
So also the reflection from the ground can be used if I actually
yeah, there will be some reflection from the ground. That is true. However, in the case of solar environment, we have non-LOS, so the power is not too much. So after reflection, the power will be insignificant. We discussed two-ray model for LOS case. For LOS case, you send I mean some good level of power towards the ground, because I mean the antenna, you need to assume here that the distance is too large. Okay, for two-ray model, the distance should be enough large, and I mean you have the radiation pattern will allow some good level of power towards the ground. Okay, so that's how you get significant power after reflection.
Yes, sir. I got it.
Okay, then spatial consistency. When we use it, then the correlation distance. Okay, update distance. I think update distance is the it is the segment size. Okay, probably update distance gives it the segment size, or sure. Or it may be the side length. Okay, when you consider okay, I'm not quite sure. The user track type is linear or hexagon, how it moves. Okay. You know what? Previously, this hexagon option was not there in the previous version. Okay. So I'm not sure what this hexagon option means, but it may represent the motion of the user along a hexagon. Okay. Moving direction, I believe it's an angle with respect to the line that you draw from the connecting the transmitter and the receiver, the initial position of the receiver. Okay. I mean, probably, yeah, you can use the direction here, where the angle means what you create with the line connecting the transmitter and the receiver. Okay, correlation distance of shadow margin, correlation distance of LOS, non-LOS conditions. There can be a consideration of an overall shadowing from, so like the foliage we are considering here to offer some shadowing. Okay, so the simulator may also consider shadowing different ways from the environment, but it will use some correlation when you use spatial multi consistency. Okay, between other, I mean shadowing among other segments. Okay, so I believe, I mean, the shadowing effects are also correlated. Okay, I mean, you don't allow an abrupt change of the shadowing. So other effects are probably also correlated. Okay, all the different effects and from the multipath environment are probably correlated. They don't change abruptly. Moving distance, how much the user moves. 40 meter. Well, let me check here. If we set it to 100, it doesn't change itself, right? Okay. Well, when it is sent moving 40 meter, the user will cover a range of 40 meter. But apparently, this distance should be within the lower and upper bound. Okay. The difference between upper bound and lower bound should be equal to or higher than the moving distance value. That's my assumption. Okay, you may check these things. It won't be possible to run too many simulations to check all different variations. Okay, then human blockage parameters. Well, again, you can turn it off, but it means that when you are holding a phone next to your ear, then if you have the base station on the other side, of course, you are also obstructing. You are an obstruction between the phone and the base station. So you can offer some blockage. Okay. In both uplink and downlink, it's actually a blockage by yourself. So, well, you can set it. There is also, I mean, rain attenuation setting here. Okay. As you increase the rain rate, of course, this attenuation will increase. Well, with all that, I think we can run a simulation. Do you want to say anything? The key attraction here is the ability of high frequency support. I mean, here it is shown 28 gigahertz by default, because I probably told you that for 5G, the most the most common high frequency use will be 28 gigahertz. Okay, the early deployments are using 28 gigahertz as their high frequency mostly. Okay, And of course, let me tell you, many high 5G deployments are not using high frequencies. Okay, but when they're using high frequencies, 8 gigahertz has become most popular so far. 28 gigahertz has become most popular, but you can set any value up to 100 gigahertz here. Well, you should mention where the output files will be located, will be saved. Okay, so the output files will include different math files. Okay, but they may not be much useful. Okay, rather the graphs will may be only useful for us, and we should give a folder location here from here, but it's not enough flexible when you locate the location of the folder. Okay, but I recommend that you always uh, direct to some folder. Okay, both text and mat file will be saving there. So we are hitting run. Okay, fasten your seat belt. You have just started running the simulation.
Yes. Sure. How to read this?
Have someone already fallen? I told you before to fasten your seat belt.
Sir,
It's
what
very
to understand
colorful.
from there, sir?
Sorry.
3D graph, sir.
That's interesting.
Yeah. Okay. So you see that I mean this axis has a distance of 40 meter because that was our setting. Okay, and at some regular segments, it has generated the PDB. Okay, and when you have a number of impulses, okay, together, so it means the environment has some may have some, say, reflector, which is taking this. I mean, a number of signals. Okay, some objects are there. Okay, so a group of impulses you have at different delays. Okay, so the tier separation. Some simulation data is also shown here. The velocity is 1 meter per second. Okay. Well, I'm not sure which figure you can see because we're sharing. Let me. Is it figure 5 or what? Figure 6? Is it figure 5 or 6?
Sir, figure 5.
Figure 5. Figure 5. Okay. Okay, and so in this case, you consider omnidirectional antennas in figure 5, and in figure 6, it's a directional antenna. I think it is for directional antennas. Yeah, it says directional antennas. So So the maximum components you can see for now you are looking at figure 6, right? So the maximum components are around -50, little higher than -50, right? So for directional antennas, we should get high values for the maximum components. For omnidirectional, it should be lower, right? So let us check the omnidirectional case.
How are you changing the figures, sir?
Just sharing a different figure.
Oh, all of them are coming. Okay, okay, okay. I understand.
Okay. Oh, sorry, it's again directional. Sorry.
How many figures
For
did you get in total?
in total 6. I'll
Okay.
show other figures too. Okay, but the key generations are this 5 and 6. So you have see power level little lower, right? The maximum component is now around -80. For directional, it was around -50. Okay, so for directional, I mean, you are confining your power towards the receiver. Okay, where in omnidirectional you are spreading in all different directions. Okay, makes sense? Any questions? Okay, as
No, sir.
okay, that's a pleasant answer for me.
Sir, what if
Yeah.
you want to
Yeah.
see any segment of this 3D graph? I mean, if I want to cut this graph into a 2D graph by
Oh,
slicing into like
oh,
40 nanosecond.
okay. That's very easy. That's very easy. I'll show you how you can convert it to 2D graph. Okay. You can rotate. Okay. So now it will become 2D, right? Sort of 2D. Yeah. It's pretty much 2D already, right?
Yes, sir.
Got it?
Mhm.
And
Sir,
you can
it's not
rotate.
helping much.
It is not helping much.
No, sir.
No, well, I mean, when you have 3D, you of course have the whole information. You have more information, right? But mm, it has generated the channel impulse response for all different segment positions. I'm not sure. There may be a way to find out PDP for a particular segment position, but I'm not sure. I'm not sure. Oh, sorry. The zooming in. Okay. So since this particular graph includes all these values, okay, so we cannot convert it to 2D. Okay, but it's possible to check the values for many. Well, it is true that the many different impulse responses make it difficult to read for certain conditions. Okay, I agree on that. Okay, and now let me share the other figures. Oh, sorry, I closed the figure. Man.
I need to run it again now.
Okay, let me share other figures first. One figure I closed mistakenly. This shows the movement of the UV or UT. Okay. In cellular environment, people usually use the term UE, user equipment. Okay. It shows how it has moved. The figure I closed actually shows the relative position of the base station. The black part probably indicates an area where you have, okay, this one is already showing. So it doesn't harm that we closed a figure. Here you have the base station and here you have moved. So the black part probably indicates high shadowed area. Okay, probably, not quite sure. Okay, previously there was a 7th figure generation, which I don't see with this version, which show a gradual path loss. Okay, and it could give a path loss exponent, an estimated path loss exponent value, PLE. But I'm not sure why they have turned off that feature. Okay, let us now run a simulation for a frequency 150 gigahertz. Do you have any questions so far?
No, sir, no question actually, because
Okay. Okay, then.
Sir, can I
Yeah.
interrupt? Sir,
Mhm.
in my case, my software doesn't, my tool doesn't have the option for penetration loss. It's by default set to no, and I don't have any option for changing.
Which loss are you talking about? Penetration loss mean human blockage or what?
No, sir. In the leftmost side, under foliage attenuation, there's the option penetration loss, right?
Yeah,
You
yeah,
can set it to yes or no, but
right.
in my case, I can't change it. It's by default set to no.
I see.
Sir, in this case, I also have the same thing. You have to turn
Yeah.
off the spatial consistency for those options to show. But in that case, the spatial consistency parameters are non-changeable.
However, we used this penetration loss while we had special consistency on.
Yes, sir.
So if we turn it off, then the outdoor to indoor options become changeable. But the spatial consistency parameters are non-changeable then.
But sir, you could change it even with special consistency on, as I have seen.
Oh, yeah. Now, well, now it has become like what he suggested. Okay. Probably, I mean, that was a bug. Okay. Initially, it showed that you could change it. Okay. So that was just a bug of the tool. I think it is more like what he suggested, that we need to probably this O2I losses didn't work when you ran the simulation.
Sir, changing the scenario works, sir. So like, sir, changing scenario to UMA and then again UMI.
Okay. Then we can do that. Oh.
Sir, I got 26 figures, sir. I don't know how, sir. I got 26 figures, sir.
Oh,
Yes,
really?
that is why I was asking you, sir. Like, how are you getting those? Then I saw that.
Well, by the way, do you see any graph with some linear straight lines, and it
No,
also
sir,
shows
it's like
clearly?
the same thing is repeated. It's like that every 5 times the same graph is repeated, sir. In my case, I only clicked run once, sir.
You know, Tassin, you are always special, you know.
Oh, no, sir. No, I'm not.
Yeah.
From 6 from sir to 26 in your case.
The software loves him. Okay, it keeps generating.
Yes.
Uh,
I don't know why.
And you are using this version 3, right?
Yes, sir. Yes, sir. The link that you gave, sir. Yes, sir.
Okay. Well, a lot of things can happen because it's a free tool.
Yes, sir. No problem, sir. I understand.
Okay. And mostly, as we experienced before, that you need to locate something here. Okay, this select a folder to save files. If you don't select anything here, then it creates problem. And sometimes when you run again, okay, then you find difficulties. So sometimes clicking reset helps, and sometimes we had to close the tool and open again. Okay.
I have closed the tool and opened again, but it's still not working. It's showing running. Please wait. I have been waiting.
Oh, did you select a folder to save files on this right end?
It doesn't allow me to select anything. It has already selected users and
No, you click on that. You double click users. Okay. You that's the point. I mean, here you have to double click and then select a folder, whatever folder you choose. I mean, in that folder, it will generate a good number of files. But you have to select a folder. Otherwise, it shows that it is running indefinitely.
Okay, sir. Thank you.
Yeah. Now we'll be using this in-house feature with 150 gigahertz. In my life, this is the first time I'm simulating 150 gigahertz. Okay. The special consistency feature has not yet been added to this in-house or in-building coverage. Okay. And there is no question of foliage or, I mean, any outdoor stuff, rain, these things you definitely don't have inside buildings.
Sir, you are not sharing your screen.
Oh, okay. Sorry. Now you can see, right? We
Yes,
have set 150 gigahertz for in-house model. Okay. The height of the base station definitely should be very low, maybe 2 meters or just 1.5 meters. Okay, let's set it to 2. Okay, so with other default settings, the environment non-LS, we're setting non-LS. Okay. The distance, should we change how much it is? Lower bound, upper bound 100 meter. Okay. Anyway, we will keep that and run the simulation. It has been running for a while. Okay, maybe we stop here. Okay, we reset. Reset doesn't work.
So you have to you have to wait
yeah.
for some time, sir, and then if it doesn't work, you have to give exit, sir, and if
Right.
it will work then, sir.
Yeah, I think we can exit and open it again. Okay. And the indications are not good.
So the exit will not work, sir. Initially, it will take a little bit of time, but then it will work.
this book tool is a development of the Rappaport team. Okay, we are our textbook. Although we are not covering much from the textbook, but the book which we have used more than other stuff is the book of Rappaport. And, Rappaport was a professor at Virginia Tech, where I graduated from, and I mean, you know what? Virginia Tech is, I mean, very well renowned for wireless communication. I mean, from the beginning of wireless communication days. Okay, one of the leaders in USA in wireless communication. But I mean, the recent status is not that high, but initially it was just top few in wireless communication. Rappaport was also here at Virginia Tech, but now he's with, I think, Purdue. Okay, he left Virginia Tech. Probably he's with Purdue now. Okay. Let's run. I didn't run the simulation for this scenario before, so I mean, I'm not sure what are the things we will get, but I can see that seventh figure here, which I spoke of. You,
Sir, you are not
which
sharing
figure?
your
Yeah,
screen.
yeah. And now you are not. You don't see any figure, right? Yeah, I'm waiting.
We
I'm
don't
just.
see your
Not
screen, sir.
you, sir.
Yeah.
Oh, sorry. I didn't share anything.
No, sir, nothing.
Well, I was forgetful even when I was young. So now I'm old. So it's well. So this is the setting that I simulated with, and you see 150 gigahertz base station height 2, and definitely I located a folder to save the files. Well, let me share the.
Sir, shouldn't the environment be non-loss?
Sorry,
Shouldn't
sir.
the environment be non-loss?
Oh yeah. Let me. Yeah, I'll run it again. Oh, this time it keeps generating like him.
Probably it will end at 26.
Looks like that. Already 19. Oh, can you see figure 19?
Yes, sir.
Okay. Okay. Good. Okay. Looks like it has stopped already. Well, this figure 19, which figure do you see now?
Sir, figure 19
there is
maximized.
Okay, just to make sure, I select it again. So here it shows the path loss for directional and for omni cases, right? Looks like the blue one stands for path loss for omnidirectional cases, and the red one for directional cases. Okay, and it gives sigma it, I was expecting PLE, but you don't see here. There's no PLE, right? So maybe it is showing sigma, where sigma is the delay spread. Okay, the root of sigma is delay spread, right? Sigma is shown in dB. So, apparently, it is showing here the delay spread. Okay, but as far you remember, the previous versions showed both delay spread and path loss exponent. Okay, the power delay profile gives you a graphical representation, but it doesn't give you the values. But this figure is to show the values. Okay, the delay spread sigma you could get, and the path loss exponent. But right now I don't see the path loss exponent. We look at other figures. Let me quickly check. So I'll be sharing now figure 4. Okay, apparently there is no motion for the receiver. Okay, it has a standard still position. So we have a 2D graph here. Okay.
So this graph we're familiar with. So
Yeah.
in examination there is.
Yeah. The 3-dimensional graph is also, it is the, it is just this 2D graph or PDP for a particular position, but then you repeat it for many different positions. But I can see PLE here. Okay, an estimated path loss exponent. Okay, and here you have the sigma or the delay spread. Okay, so this figure gives us better values. Okay, well, now it's better also in the respect that with 3D graph we couldn't get these sort of values. Okay, that's why I was more thinking of figure 7. Okay, another figure from which we could get some values. Okay, as engineers, you could with only graph it is difficult to work. You need some values. Okay. So, but now you can see here the total path loss is estimated as 101.5 dB. The receipt power is shown minus 71.5. I'm not sure, but it may be some average power. Oh, let me see what it is. Here we have minus. Okay, it is the peak power, right? Minus 71.5 is probably the peak power that we have here at, at the middle spike. Okay. Overall path loss exponent. Okay. So this gives us pretty good values. Okay. Questions? Any questions about this figure?
Sir,
The delays.
did we simulated a particular environment? I mean, maybe the reflector or the environment may be changed in different cases.
We don't have much control over the environment. Only a few things we can adjust. Let me go there. Like the atmospheric conditions, you can adjust the base station height, the user terminal height. Okay. Otherwise,
but the number of
environment, no, I mean the propagation environment, it just generates.
randomly.
Yeah, it generates something as the propagation channel. Okay.
So then we can't use actually this in real life. I mean, if anyone wants to simulate anything.
Well, you can, because it simulates some typical scenarios. Okay. Say we have say if we consider this urban macro, rural macro. Okay. So these are based on extensive tests in typical urban microenvironment.
Yes.
Typical urban environment with medium-sized cell. We had a discussion shortly in our theory class on path loss models. Okay, there we are supposed to mention these things, that the first significant test to check the reception, okay, in different types of environment was a test done by Okumura in Japan, and he did it in Tokyo. Okay, it's because the most of the revenue comes from the city areas. Okay, so the operators are more focused on the urban or city areas. So the tests were also done mostly for city areas, especially in the beginning. Okay. And Okumura model was used for a very long period. Later, some other modifications were added. Okay, so many other cities actually use the same model. It is not exactly like Tokyo. It will not resemble Tokyo in full, but to some extent it matches. Okay. So what the operators in practice does, they use some particular model. They first take some particular model. I mean, if you have, if you join the radio network planning team, okay, of an operator, then you'll find these things. They first pick a model, but later they tune. They do some tests for their city, and depending on the test results, they tune the model. Okay. So that's a slight modification of the model. But here, it is, but we can still call it valid. Okay, because it will give you results for, that is close to your real life expectation. And that is why you need different types of scenarios. Okay. What else?
Nothing. Fine, sir.
Well, then you should practice this tool. Okay, everything we are sharing here, say the Cambium network tools. On the next day, we'll demonstrate another tool from Cambridge network, which simulates Wi-Fi. So all these tools you should practice more than I have done. Okay, so that you become a better expert.
So for
For
practice
what?
in terms like
I'll tell you. I'll tell you the reason. Okay, some of you will be joining this university shortly, right? Many of your senior brothers have already joined this year. Brothers and sister,
yes,
yeah, have already joined. You may have already got this information along with some sweets. I believe
no sweet sir, online is sweet candidate,
this
sir.
information.
It's very heavy, sir. Very happy, sir, because you will be one of them.
After lockdown, we are going to those big
April. Okay, yeah, okay. Then I mean, you're just like me. Okay. So once you join this university, okay, you may have to demonstrate this tool to the students, and I really want that you do a better job. Okay, so I urge upon all of you to practice this tool more than I have done, to go through the manual more than I have done, learn better than I have done, and so you can help the students better. Okay. What else?
Sir, for practice, you mean different parameters? I will
Yeah,
change
yeah.
different parameters and see
Right.
what happens. And
Exactly, right. For different settings, please check. And if you have some good experience, okay, I mean that we should all know, then please share it with us. Okay.
So when we split, so basically which figure should we compare between them?
The most important figures are, see, the first few figures, figure 1, 2, 3, show you the input conditions, how the UT is moving with respect to the base station position. Okay, the first three figures show these things. Then it shows PDP, and this is most important for us. And finally it shows a figure, but that we found that for other scenarios it didn't. Okay, but it shows a figure which gives you the path loss with distance, how the path loss is increasing. So that should have a straight line profile. Okay, any other questions?
No, sir.
no, sir. Only, sir.
Okay, then we wrap up today. Thank you for your time.
Thank you, sir.
Thank you very much.
Assalamu alaikum.
Alaikum salam.